When a force is applied to an object, it can affect its motion. It can cause it to accelerate in a particular direction. So what happens if we apply more than one forces to an object? It's not like an object can start moving in two different directions at the same time. When we consider all of the forces acting on an object at the same time, we can imagine them coming together into one overall force that kind of represents the total effect that all of the forces are going to have on the object. And we call this the resultant force. So we're going to have a look at a few examples of how we can draw some free body diagrams and then how we could use that to calculate resultant force. Let's start off with a falling ball as an example. I love bouncy balls, apparently. I always use this as an example. So we've got a bouncy ball falling towards the earth. What forces are acting on it? Well, first of all, we've got the weight of the ball pulling it downwards. Let's say that's 1.5 newtons. And since force is a vector, we can represent it with an arrow. And the size of the arrow represents the magnitude of the force, so 1.5 newtons in this case. And the direction of the arrow obviously represents the direction. So we've got that 1.5 newtons of the weight, and there's another force acting on this. We've got air resistance, which will always oppose motion when something's moving through air. So the ball's falling down, so the air resistance is acting upwards, so we can represent it with an arrow like this. Let's say it's got a magnitude of 0.7 newtons. So this is called a free body diagram. A free body diagram is where we just draw all of the forces acting on an object and represent them with arrows where the size reflects the magnitude of the vector and the direction obviously. If I want to use a diagram like this to try and draw the resultant force, so combine all of the forces acting on the object, all I have to do is redraw these arrows one by one and start each one from where the previous one ended. The resultant force will then be a single line draw from where I started off to where I ended up. That might sound a bit confusing, but it's really simple. Let me show you how we do that with this ball. So if we're going to draw all the forces one by one. We'll start off with the weight, so that's going to be an arrow like that. And then where we finish that, we're going to draw the next force. So starting from there, we're going to draw the air resistance, which looks like that. And there we go. We now connect where we started here to where we finished here with one arrow, and that is the resultant force. So that will be 0.8 newtons acting downwards. And you might look at this example, some simple examples like this, you might think you could work that out in your head. Absolutely. If the two forces are in opposite directions, the resultant force will be the difference between those two forces, and it will be in the direction of the bigger force. If you've got two forces in the same direction, the resultant force will probably be them added together. You can imagine that, stacking those arrows on top of each other. But anyway, let's look at a slightly more complicated example. Let's look at a car setting off down a road. So let's do the forces acting on this car first of all. We'll have the weight, let's say that's 10,000 newtons acting downwards. We'll have the reaction force from the road, keeping it pushed back up. That's going to be 10,000 newtons upwards. We're going to have the driving force from the engine. Let's say that's 5,000 newtons pushing forwards. And we're going to have air resistance pushing backwards. Let's say that's 500 newtons. So there's our free body diagram for a car setting off down the road. Let's try and draw the force diagram now to resolve the resultant force. So again, we're just going to draw these arrows one by one, starting where the previous one finished. Let's do weight, driving force, reaction force, and air resistance. So now, once again, the resultant force just goes from where we started to where we finished, like this. It's going to have a magnitude of 4,500 newtons. So you can figure out the magnitude either by having some scale, like say 1,000 newtons equals 1 centimetre, for an example like this maybe, or you could even just work it out. So you can sort of use geometrical arguments and you can see that the magnitude of this resultant vector is going to be the difference between this 5,000 and this 500, like that. As I'm editing this video, I realised that I've done something a bit silly. This force diagram that I'm showing here is technically not correct. The arrows aren't to scale. It's because it was really difficult to draw the force diagram to scale and still have it be clear on the video. But I just wanted to point out that technically it should actually look like this. And I know that's a bit less clear. These arrows are a bit weirdly sized because of the forces that I've chosen. just be aware when you're drawing a force diagram, you need to make sure that the size of the arrows scale relative to the magnitude of the forces. Right. We can even resolve forces that aren't necessarily in the same direction. I know we just had an example there, but the up-down ones cancelled each other out and we were left with just the left and right ones. What about an example like this, where I've got a force acting to the left and I've got a force acting upwards? Again, we would just draw them end to end, so we'd end up with something like this. The resultant force is now going to be at an angle, because we're connecting where we started to where we finished, like this. And if you wanted to calculate what the length, what the magnitude of this resultant force is going to be, you could use Pythagoras's theorem. You could measure it, like I said, if you've set a scale for the previous two arrows. Yeah, it's not much more complicated. You just need to use a bit of trigonometry in that case.